for which it is also tested in your alternative assessment, your WA2. Okay, we are going to be now looking at another type of graph that is water depth versus time. Okay?
Wow.
Water depth. Okay, now let's read the question together. Alright? It says that there are 3 containers that were initially empty, and each of them are being filled with liquid to a height of 8 centimeters by a tap at constant rate. So you imagine having 3 different containers, tap on top, it is being filled up. The rate at which it is being filled up is the same. That means that your water, okay, your water tap itself, when you switch it on, okay, the water comes out at the same rate itself. Okay? Then after that, the next line says that the graph in part A shows the height of the liquid as the container is being filled in seconds. Question 1 wants you to explain why the graph is a straight line for part A. And then in question 2, it says to fill up the graph for part B and C and also explain the phenomenon for the graphs. So we take a look at this first. Okay, we have a container that is a cylinder. It doesn't matter whether it is cylinder or not. Okay, but in this particular case, because of the uniform structure of it, okay, it doesn't change its shape as the water is being filled up. The rate, the height at which the water actually changes, okay, the rate at which the height changes, it is actually the same. Right? So to help you visualize this idea, I want to show you this animation here. Okay? So in this case, instead of a cylinder, it's probably maybe a cuboid, doesn't matter. But what we see is that it is a uniform, okay, height as we go up from one layer to the next layer. So look at this animation. Before I play the animation, I just want to verify that later on when you see the graph, it starts off kind of slightly away from the y-axis. Okay, it is just a problem in the animation, you can ignore that. Right, so I'll start. So you see the water is being filled up, okay, and we're getting the same straight line. Okay, the straight line doesn't change at all. I refer to this gap over here, you can ignore this gap. It is supposed to start right at the origin. Okay, and why is it that this happens? Okay, so in your notes, it says that the graph is a straight line because the container has a blank, right? Okay, and that is because there is a uniform cross-sectional area. Okay, the cross-sectional area as it goes up. So if I were to slow this down, okay, for each layer that it increases, so I'm doing this in a very slow and exaggerated manner, each layer that it goes up, right? Okay, because that particular layer is the same size as the previous layer. So the rate at which it is being filled is the same because your tap doesn't change, right? Therefore, it must be a constant rate at which the height increases. Hence, this is the kind of graph that we're seeing. Okay? So this is a very slow rate now. Right? Let me just get this over and done with. Okay, now what if I change the container to be something like that, whereby the bottom layer is something slightly wider and then the top layer is something that is slimmer? How will the graph actually look like? What do you think? Let's just do a thought experiment in our head. Will it be slower or faster at the bottom? It will be slower, right? Okay, because the base itself is wider, it will take a longer time to fill up that area itself. It should be slower. So when we're talking about slower speed, right? What should the tangent look like? Steeper or gentler? It should be gentler, correct? So we go with the concept, recognizing that the bottom being wider, it should take more time. That means slower, and therefore your tangent or your straight line itself should actually be a gentler gradient. So we will be expecting something like that probably. Okay? So whereby the first segment is for the bottom layer and then the next segment should be the top layer. Okay, so let's take a look at the animation here. I only have something like that. Okay. Okay, so the narrower one will definitely be faster. Okay, so go with your logic. It is logical, right? Okay. Alright. Okay, so the explanation. So the graph actually consists of two segments or two straight lines. So the first blank is two straight lines, of which the second line is actually steeper. Okay, that's for the second blank. And the third blank, it is because the container can be segmented into two parts. Of different uniform cross-sectional area. Okay, and then also the bottom part has a larger cross-sectional area than the top part. Okay, so that will be how we explain it. Okay, in order to fit into that graph that I've drawn for you here, okay, so maybe to fit, in order to show the distinction, down here should be steeper, down here should be gentler. Okay, something like that. Okay, because it's supposed to end at where time T2 is. Okay, move on. We look at the third one. Okay, third one is kind of like a truncated cone. Okay, it's a vase kind of thing. So what do you expect this is going to look like? So in this case, it's not like it is segmented into two distinct parts. The cross section is actually not all the same as well. Okay, there isn't a uniform cross sectional area. So what can we see? What do you think we can expect out of this? Exponential. So Kim Yu is saying something like that. Let's think about this. Okay. Do you think this makes sense? How does the tangent behave? Okay, if I were to draw my tangents, it is going from gentle to steep, right? So the other way. Okay, maybe I'll draw. My black marker is not working. Let me get another one. Okay, so Kim Yu say the other way. I suppose the other way might be like that. Okay, so we need to think along the lines of a tangent. So in this case, for our tangent, right, this one looks like this here, and then after that it goes like that. So this one here goes from gentle to steep. While here it goes from steep to gentle. If I were to look carefully at this container that we have here, the one at the bottom is of a smaller cross-sectional area, while the one at the top has a bigger cross-sectional area. So with a smaller size, it should take a shorter time to fill up. Alright, so it should be faster. And therefore, we should be expecting something that's of a steeper tangent. So therefore, this second graph is what we should be expecting. Okay, so I'll show you the animation. Okay, this diagram here is a cross section, that's why it's of this kind of shape. So, okay, because every layer is different, it is not a uniform cross section. Therefore, it must be a curvature already. Okay, it must be a curvature. Okay, so therefore we are looking at something like that. Okay, so if I were to draw it into this diagram, okay, you need to sketch a diagram that is of this shape. Okay, so to explain it, we will say that since the cross-sectional area of the container is non-uniform, and increases. Okay, the area itself increases as your height increases. Okay, the graph consists of a curve that becomes less steep as the container gets wider at the top. Okay. Okay, I hope that this convinces you in terms of the logic aspect, rather than having to always memorize, because there will be always too many diagrams already. Okay, do you want to see the other animation? Yeah?
Yes!
Wait up. One is kind of actually it doesn't matter what kind of name you have. I think this one is more algorithm. Then we will learn it. Okay, so looking at this one, what do you expect it to be?
My first choice.
Getting faster, right? The first choice one, so let's check. Okay, so it's getting steeper as it goes up. So let me erase this up. Okay, then what about the spherical one? Okay, sorry, I think this is the best the software can create. Okay, imagine there's a sphere. What do you expect it to be?
Second choice and my first choice.
It will start off slow or fast. Start off fast, right? Because the cross sectional at the bottom is smaller. Okay, so it starts off fast, then after that it's getting slower as it progresses up. Then this one it will become constant. Then after it will get faster, right? Okay, sorry, actually I shouldn't say that it starts off fast. It starts off slower, okay, because it's getting wider. Then uniform. Then after getting faster, right? So how would we expect the graph to look like? Okay, it will look something like that. Okay, so we observe the tangent. It is getting slower, right? So at this juncture, this tangent compared to this tangent over here, it is getting slower. Then later on, in between, it becomes a constant somewhat. Okay, then after that, from here to here, it is getting faster. So we see that the tangent here versus the tangent here, it is getting steeper. Then all the way to the top. Okay. Okay, let's see what about the last one. What do you think the last one will look like? Okay, so it progressively becomes faster, then after that when it goes up to the second segment it becomes slower, right? Okay, so this will be how we expect the graph to look like. Okay, the stretch one is just about how narrow the graph is like. Okay, yeah, it just makes things wider, that's all. Okay. Okay, any questions?
No!
Alright, great. Okay, so let me just exit this and go back to our notes. We take a look at example 24. Okay, come back to reality also. it shows three containers with dimensions that show the containers are initially empty, and it takes 20 seconds to fill each container at a constant rate. So all the containers take 20 seconds. Okay? So it says that the diagram below shows the relationship between the depth of the liquid and the time in seconds taken to fill container A. So we have this over here. On this diagram, we want to draw a sketch for container B and container C. Okay? We see that container B looks very different from container A. We expect differences. Okay, the base is also different. Now, the graph that we are given, the grid is actually an accurate drawn to scale one. Okay, we are able to do the necessary calculations to know precisely at what time will it actually complete this part of container B. Okay, because at the end of it all, we know that it will fill up in 20 seconds. So starting from the bottom all the way to the end, it should be from 0 seconds to 20 seconds. But how will it look like? What time will it be when it arrives here on container B? Okay, so we do our necessary calculations. Okay, so given that it takes 20 seconds to fill the container at a constant rate, we need to first find out what is the rate of filling. Okay, the rate at which the water flows in. So that can be calculated by the fact that we know the volume of container A. Okay, it is 20 cm wide at the base, and then the depth is actually 10 cm, and the height is 50. So the volume of container A divided by the time taken, which is 20 seconds, will give us the rate at which it is being filled. Okay, so the volume of container A will be 20 times 10 times 50. So it is being filled at a rate of 500 cm3 per second. Okay. Then we need to determine how long does it take to fill up container B up to the first 30 cm height. Right? So this actually tells us that 1 second it can fill up 500 cm3. This is what the rate is telling us. Okay? If I can tell what is the volume for the bottom segment of container B, I will be able to know what time is it going to be at this height. Alright? So the volume of the bottom segment is actually 30 times 10 times 30. And that will be 9,000 cm3. Wow. Okay, so the time taken to fill up bottom part of B will be 9,000 divided by 500. Because 500 cm3 only requires 1 second, so now it's 9,000. We just divide by 500, we will get 18 seconds. Okay, done? The depth here is 10 cm. Yeah, so everything 30, 10 is all inside is 10. Okay. Alright. The remaining portion, do we need to calculate? Don't need. Why? Because total is 20 seconds, right? We already know down here is 18 seconds, the remaining will just be 2 seconds. Okay? Understand? Because the question already said all the containers are being filled up in 20 seconds. Okay? So now to draw the accurate graph, let me just scroll this up. Okay? So in 18 seconds, I'm able to reach a height of 30 cm for container B. So this is one point that will be important. Okay? Then after that, reach a height of, what was it, 50 cm, because the next remaining part is 15. All of it has a height of 15. So therefore, use a straight line ruler, or a straight ruler to draw your straight line. Okay, so this will be your container B. Over here is your container A. Okay. For your container C, right? Because it is of this shape. Okay, it is not a uniform cross-sectional area. So you may not be able to draw it very well, but you get it in your notes. Okay? Because it is not a uniform cross-sectional area in which it is being filled up from the bottom to all the way to the top. So therefore, we're expecting a curvature. So as we go upwards, is it getting slower or faster? Faster, right? So therefore, we will expect that the tangent starts off slow, then after it gets fast. So therefore, our graph, in this case, should be a curvature. I do not know how the curvature is like. This is really just an estimate. Okay? So this one, there is no accurate points that I can go and calculate, because it is a non-uniform cross-sectional area. Questions? We do one last one. Example 25, so that we are done with the same type of question. We look at example 25. Okay, let me zoom in now. Okay, example 25. Dash, I didn't allow you to go toilet, doesn't mean I have to use sleep. Okay, the diagram below shows 3 containers of a fixed volume, varying cross-sectional area, each with a height of 8 cm. So all of them are of the same height. The containers were initially empty. Each of the containers was then filled with water by the same tap and constant rate. Given that it took 60 seconds to fill each container, so that means at the bottom it starts off 0 seconds, at the end we're looking at ending off at 60 seconds. We want to sketch the graph of the height of the water level against time for each of them. Okay, so we're just going to draw them separately rather than all in the same axis. Okay, so for part A, the first one, how will we go about drawing our graph? Okay, now we see that in part A, right, the 2 segments actually are of a uniform cross-sectional area. So we are expecting a straight line to be drawn, and we can calculate this because we know the total volume. Okay, or rather we can go and calculate the total volume. Perhaps it is not numerical in value because of the fact that our radius is given in x. Okay, but we can calculate something out. Right? So let me just do the working here. For this particular segment over here, okay, what is the volume of cylinder formula? Pi r squared h, okay? So pi r squared h, this one is diameter. So in other words, the radius will be 2x and the height is 4. Okay, and this will give us a volume of 16 pi x squared. Okay, for this one over here, the diameter is 2x. So pi r squared, radius is x, times the height, it will also be 4, because 8 cm minus 4 cm. And this will give us 4 pi x squared. So the total volume in this case is a total volume of 20 pi x squared. Okay? The question says that it is being filled up in 60 seconds. We can do it in proportion by proportion. So in this case, 16 pi x squared divided by 20 pi x squared. Okay? This volume divided by total volume times 60 seconds will be able to tell you that this requires 48 seconds to be filled up. Okay? So for this part here. And then for this segment over here, because total is 60 seconds, alright? It's just 60 minus 48 normal. Okay, 12 seconds. So this will help us be informed over how my graph is going to look like. Yeah, that sounds terrible. Okay? We expect it to be steeper for the second segment, gentler for the first segment. We need to indicate the important values. 48 seconds here, 60 seconds here. This will be a 4, and this will be a 8. Okay? For part B and part C, we are not able to determine because we don't have sufficient information. But we know that for part B, the bottom segment, okay, has a uniform cross-sectional area. So uniform cross-sectional area would mean that we expect a straight line segment, okay, followed by a curvature because of this non-uniform cross-sectional area. Okay, it is getting slower and slower as it goes up because the cross-sectional area is getting wider and wider. Okay, so we will expect that the tangent itself is getting gentler. You cannot draw your graph to look something like that. As mentioned in the distance, time, and speed time graph topic, your graph needs to be smooth. Okay, so therefore, okay, you might need to have it such that it is straight over here, then gently curls out. Okay, so to indicate the key information, we do not know this information. So I'm just going to indicate cannot be determined for your info. And then the height here will be 4 cm. Then once it reaches the end, it needs to be a 8 cm in height and 60 seconds in total.